Hello friends, and welcome back to Kitchen Chemistry. I have been requested to do some concentration calculation videos, so I'm going to do a few examples of those. I am going to be doing problems from this worksheet. This is the concentration calculation worksheet that's in the Google Classroom. I'm going to be doing question 1, which is a molarity question. I'm going to be doing question 3, where I'm going to do it first percent by mass, and then I'm going to do the same question again in parts per million to show you how to do that. And then I'm going to do this last challenge problem down there at the bottom. So this is going to be kind of a long video, so hang with me for what you need. Leave after you get what you need, and feel free to go practice on your own. The equations that we are going to need are on the reference table, and this is our equation for percent by mass, and our two concentration equations for parts per million and molarity. Percent composition is a much more universal equation that you can use for other things besides concentration, but it works for concentration too. So, boom, boom, boom. This is what we're going to be doing today. All right. So, okay. Question 1. Question 1 states, what is the molarity of a 0.5 liter solution that contains 0.5 moles of KNO3? So let's just break this down and see what we have in the equation, okay? So we know that the volume of the solution is, whoops, excuse me, got my phone hanging from my cabinet, so try not to bump it anymore. Volume equals 5 liters. And the mass, the moles of solute is 0.5 mole KNO3. I promise I'll be cleaner for the rest of this. So, if we look at our equation for molarity, the equation for molarity is moles of solute divided by liters of solution. We have moles of solute and we have liters of solution. So molarity, capital M, equals our moles of solute over liters of solution. And if I plug in my values, we have 0.5 moles divided by 5.0 liters. And we get 0.1. 0.1. And now it's important, what are our units? Well, our units, we have moles divided by liters. Nothing got canceled, so we're going to keep both of them. And our unit becomes moles per liter. Or we can also write that as 0.1 capital M. Both of these are correct. You can use moles over liters, or you can use capital M. Capital M, it makes you look a little more like a scientist, so this one's fun. So the molarity of 1/2 mole of KNO3 dissolved into 5 liters of solution is 0.1 mole per liter of solution. Okay. Let's move on to the next question. We'll do question 3 now. So instead of doing how much solute, how many moles of solute do we have in the solution total, and what's the volume of the solution, we're just going to mess with masses now. So when you put sugar into water, or you put salt into water, the volume of the water doesn't really change because it gets dissolved throughout the liquid. But the density does change. The mass is still there, conservation of mass. That is why salt water and fresh water are different densities. So when you have fresh water flowing into a saltwater ocean, you have these areas of the ocean where there are very interesting like mixed currents, and some water is being pushed down and some being pushed up, and it's because of temperature and density differences. So another way that we can calculate concentrations is by mass, which is going to affect the density. So this problem states, what is the percent by mass of a solution prepared with 34 grams of potassium iodide and 26 grams of water? So our solvent is 126 grams, and our solute is 34 grams. So if our solvent and our solute have these masses respectively, then the solution, both of them mixed together, equals 126 grams plus 34 grams. And that, if I'm not mistaken, is 3160. 160 grams. Okay? So these are the masses: solvent, solute, and solution. So we have three numbers. So we got to figure out what are we going to use in our equation. So let's look at the percent by mass equation. And it is the mass of the part versus the mass of the whole. So this is written in a way in your reference tables that's universal to all percent by mass compositions. So what is the part of this question? Well, the part, we want to know the concentration of solute. So the solute is going to be our part. And what's the mass of the whole? Well, the whole, everything together is 160. So we want the mass percent by mass equals mass solute over the mass of solution times 100%. So let's plug in our values. We have 34 grams divided by 160 grams times 100%. 34 divided by 160 equals 0.2125. What's our sig figs? Okay, so here we have 2 sig figs. Here we have 3. So I'm going to round this to 2 significant figures, 0.21. And what is our unit here? Well, grams has canceled out grams, so we don't have grams anymore. So 0.21 times 100%. What is our final value? Well, we're going to move the decimal point 2, and we get 21%. And the solute was potassium iodide, so 21% potassium iodide by mass. Okay, that's our final answer here. Now, lastly, we did this in percent by mass, but there's another method called percent by, or parts per million, which is very similar to percent by mass, but a little bit different. So, if you look at the equation, parts per million is the mass of the solute over the mass of the solution. Interesting, mass of the solute over the mass of the solution, okay? But instead of being times 100%, it's times a million, all right? So we want parts per million. A percent is really just parts per 100. If you get 50% of a assignment correct, that's half of the assignment. So if you have 500,000 parts of a million, you have 50%. So parts per million and percent by mass are essentially the same thing. We're just using a different like part count. So the bottom of the fraction of the equation, or sorry, not equation, the bottom of the fraction, instead of being 100, is a million. So our proportions are going to stay the same though. So let's take a peek at this. All right. So here's our setup for percent by or for parts per million. Okay, and it's so similar to percent by mass that I'm just going to make the changes in red. Okay, and everything else that stays the same is going to stay the same here. So for our next step, right, we're just going to plug in 34 grams divided by 160 grams times 10 to the 6th. So this is going to give us 0.21 times 10 to the 6th, and this is going to give us 21.21 times times a million. There we go. 210,000 parts per million. Okay, so now let's examine how close this parts per million and percent by mass thing is in terms of like ratios, because mixtures and concentrations are all about ratios. And 210,000 looks extremely different than 21%, but let's talk about how it's not that different. And I'm going to do that by talking about parts per million and percents and what that actually means. So percent by mass, and here we have parts per million. Over here we had 21%, and over here we had 210,000 parts per million. So what does a percent mean? Well, a percent means out of 100. That's really what it means. It means, can we take some decimal or ratio or fraction and turn it into an out of 100 term? Because out of 100 is really easy. Money is out of 100. It's just like we use that kind of scale all the time. Metric measurements are all based on tens and hundred scales, so it's a really convenient way to do things. So if we talk about this as out of 100, this is 21 out of 100. Okay, so what does parts per million? Well, let's focus on this back bit here, per million. Out of a million. So let's do the same thing and rewrite this out of a million. Okay, so let's simplify this. And we just cross out zeros to simplify. So we have 4 zeros here. We have 4 zeros here. Oh Lord, what just happened? Simplify it again. 21 out of 100. They're the same thing, okay? The ratio hasn't changed. It's just a different unit. Parts per million, percent. Out of 100, out of a million, basically means the same thing.